Good evening, guys. Am I audible?
Yes, sir.
Sir.
Okay. So what was the last concept which we discussed? Where did we stop in the
Sir,
previous?
specific cases for the potential energy of a dipole and external electric field.
Potential energy of a dipole in external electric field, right? So just give me a minute. So all of you have your textbook with you?
Yes, sir.
Yes, sir.
So this was the last concept we saw, no? Potential energy of a dipole in external electric field.
Yes, sir.
Correct.
Yeah.
Now we are going to move on to the next part of this chapter, which is going to be the capacitance. But before we understand the capacitance, right, we need to understand another concept called as electrostatics of conductors. Okay. So the next heading is going to be about electrostatics of conductors. Right. So for that, there are 6 properties that are exhibited by conductor, which we need to understand. The first point is, inside a conductor, the electrostatic field is 0. So when you take a conductor, inside the conductor, electrostatic field is going to be 0. So meaning of it is, suppose I take a conductor of this sort, right? And I place this conductor in external electric field. So if I place the conductor in external electric field, what will happen in this scenario is, listen to this carefully. See, inside a conductor, you have free electrons. So what is present inside a conductor? You have free electrons. So what will happen to those free electrons when they are subjected to a force? So all those free electrons will get drifted to the left. Why is it so? Because we know that negative charges will experience a force in the direction opposite to the electric field. So all the negative charges will get drifted to the leftward direction, as a result of which you'll be left out with positive charge here. You'll be left out with positive charge inside the conductor in such a way that inside the conductor, there will be an electric field that is induced in this direction. Understand, listen to this concept very carefully. It's a very, very, very important point. I have a conductor. I take the conductor, I place it in the presence of external electric field. When I do that, the external electric field will penetrate into the conductor, right? As a result of which the electrons which are present inside will get drifted to the left. So there will be an induced electric field which is traveling from the positive to the negative charge. And there is already an external electric field from the negative to the positive charge. So the external, this E is there, no? That is already existing in the rightward direction. in is not inside, it is induced. So induced electric field will be in this direction. In such a way, if you try to calculate the net electric field in this scenario, it will come to be electric field due to the outside value plus negative of induced value. Why I'm using minus sign is because it is in the opposite direction to the given one. So the value of net electric field inside is going to be 0 because the induced electric field will exactly be equal to the external electric field. As a result of which, the net electrostatic field inside a conductor is going to be a 0. The net electrostatic field inside a conductor is going to be 0. So this is the statement which is given in your textbook. You can underline this part. A conductor has free electrons. As long as the electric field is not 0, the free charge carriers, the free electrons which are present inside the conductor would start experiencing a force in the leftward direction. They get drifted to the left. And the positive charge will be to the right, so that the induced electric field in this scenario is going to be 0. Sorry, induced electric field will be exactly equal to the external electric field. Hence, the net electric field inside is going to be a 0. That is a point that is to be noted. Is this clear? As I told you, this is a very, very, very important point. Right? Okay. Next. The second point is, when you have a charged conductor, right? So when you charge a conductor, at the surface of a charged conductor, the electrostatic field will always be normal to the surface at every point. Means if I have a conductor like this, when I have a charged conductor, first thing that is to be noted is, see, I'm borrowing this point from the third one. The interior of a conductor can have no excess charge in the static situation. The interior of a conductor can have no excess charge in the static situation. So hence, all the charges that you are going to give will go and sit on the surface of the conductor. So when they sit on the surface of the conductor, what will happen is, let's say if I take the electric field to be in this way, and if I draw a tangent at this point, let's say it is theta, then this is going to be E cos theta, and this is going to be E sin theta, right? So if I place a test charge here, right, had the E cos theta component existed, then the test charge on the surface would have not been stationary because it will experience a force of Q into E into cos theta. As a result of which, it would have started moving on the surface of the conductor. When it starts moving, right, then what will happen is the static condition is lost. See, when something is moving, right, it is going to be dynamic. It is not static. Means if that E cos theta existed, then the charge would have started moving, as a result of which Q E cos theta would have not been a non-zero value. But for the charge to not violate the static condition, what should happen is E cos theta is supposed to be a 0. So when E cos theta is 0, then cos theta is going to be 0 and theta is going to be equal to pi by 2. As a result of which, the electric field is always perpendicular to the surface of a charged conductor. Okay, the electric field is always perpendicular to the surface of the charged conductor. Okay, next. The third one is the interior of a conductor cannot have any excess charge in the static situation. So when you take a conductor, in the static situation, the interior of the conductor can have no charge stored in it. Okay, it will have no charge that is stored in it. It's because if you consider a Gaussian surface here, if you consider a Gaussian surface just inside the conductor, then what does Gauss law state? The net electric flux is equal to the total charge enclosed by the surface. But when there is no electric field itself present within the conductor, right? When there is no electric field itself that is present within the conductor, can I say that the flux is going to be zero? So when the flux is going to be zero, that implies that the charge enclosed is also going to be equal to zero. When the charge enclosed inside the surface is zero, where will the excess charge go and sit? There is no other option other than going and sitting on the surface of the conductor. So this is what is given. This means that there will be no net charge at any point inside the conductor, and whatever excess charge you're going to give, it will always go and sit on the surface of the conductor. Okay, it will always go and sit on the surface of the conductor. Okay, next. See, are you guys able to understand?
Yes, sir.
Fourth one. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. So we know that the net electric field inside is zero. When the net electric field inside a conductor is zero, observe, we know that E is equal to minus dV by dr. So when electric field inside is going to be zero, can I say minus dV by dr is going to be equal to zero? And we know the fact that the derivative of a constant function is always zero. So from here, what is the conclusion I can do is this implies that the potential is going to be constant throughout the conductor. And what that constant is going to be equal to is potential will be exactly the value that is present on the surface of the conductor as well. One minute. So I hope you made a note of this point. Electrostatic potential is constant throughout the volume of its conductor and has the same value as that on the surface, right? Next is fifth one. Electric field at the surface of a charged conductor is E is equal to sigma divided by epsilon naught. Okay. So if you take a conductor like this, on this conductor, what we'll do is we'll consider a Gaussian surface in such a way that half of the Gaussian surface is going to be inside the conductor below the surface and half is going to be above. Right. So we know that all the excess charge is going to go and sit on the surface of the conductor. So here also there will be some excess charge. Due to this excess charge, the electric field is going to be in this way. Okay. So if I take this area to be A, then E into A is equal to, right, the charge enclosed divided by epsilon naught. Why? Because flux is equal to the charge enclosed divided by epsilon naught. So E into A is going to be EA only. This will be equal to, what is the charge enclosed by this? The charge enclosed by this will be sigma into A divided by epsilon naught. A and A will get cancelled. Electric field will be sigma divided by epsilon naught times n cap. Why sigma by epsilon naught times n cap? Is because sigma by epsilon naught is a value. N cap is going to be the unit vector, which is in the perpendicular direction to the surface. Okay. Is it clear?
Yes, sir.
No. The last part is called as electrostatic shielding. So as the name suggests, no, shielding is protection. So what will happen is, if you consider a conductor, if you consider a conductor with cavity with no charges inside the cavity, right? With no charges inside the cavity, then what you can observe is, right? We can observe that the electrostatic field inside, the electric field inside it is again going to be a zero. As a result of which, what will happen is the outside surface will start behaving like a protecting membrane for the cavity. Okay, you're able to understand what I'm trying to say. So if you consider a conductor with cavity, the best example for that is your lift, right? In your apartments, if at all you go through a lift, right? When you try to have a phone conversation, whenever you try to have a call, right? You can see that most of the times you'll not be able to speak because the signal will not be clear. And the reason for that is this concept of electrostatic shielding is getting applicable there. Are you able to understand what I'm saying?
Yes.
So this is what happens. So electrostatic shielding means the conductor acting as a protection for the outside charges to enter the system. The other example for this is when there is a heavy lightning that is taking place, right? When there is a heavy lightning that is happening, you might get a question like this. Is it safe to sit inside a car or is it safe to stand under a tree? So what do you think is the answer? So is it safe to sit inside a car or is it safe to stand under a tree?
Sir, it's safer to sit inside a car
Why?
because of electrostatic shielding.
That's it. Because cars are made up of metals. So metal outside layer is conductor, inside is cavity. That is where we are sitting. So the charges cannot touch us, right? Whereas when you stand under a tree, you are always under risk. Are you able to understand? So this is how it works. Okay. So this concept of electrostatics in conductors, with this we are done with the first part, that is the electrostatics of conductors is done. Now we need to understand the concept of what is happening with dielectrics, because this is going to lead to the concept of capacitors. Means for capacitors you need to know both the things, what happens within a conductor and what happens in another material called as a dielectric. So I'll tell you what they are. So basically, when you talk about a dielectric, dielectrics are non-conducting substances. Okay. So what happens here is, in contrast to conductors, conductors have free electrons. Here, we don't have any charges. Right? They do not have any charges. I mean, they do not have any free charge carriers. So what is present inside dielectric is, you'll be able to find small dipoles that are existing. You'll be able to find these small dipoles that are dielectrics in such a way, it is going to look something like this. If I take a dielectric, for instance, then you will have small dipoles present like this. So one dipole will be like this, negative and positive. There will be another dipole, negative, positive. There will be another dipole, negative, positive. There will be another dipole, negative, positive. Like this, you will have many such dipoles present. Okay. And when you place this in the external electric field, when you take a dielectric and place it in the external electric field, right? Now, what happens is, these dipoles, the presence of external electric field, experience torque. We know this concept from the previous chapter. They experience torque and they start rotating. After a certain instance, what will happen is the dipoles will get aligned like this. There'll be negative here, positive here, negative here, positive here, negative here, positive here. Right. It will happen something like this. In such a way, okay, in such a way that if you take the charges here, the total charge will come out to be 0. Right. So remember, there is an external electric field E existing. So there will be an external electric field E existing here. And due to the end charges that are present, there will be an induced electric field which is happening, which is appearing exactly in the opposite direction, such that when you calculate the net electric field, it comes out to be E plus negative of E induced is equal to a non-zero value. Means this value is not equal to 0, like how it happens within a conductor. So within a conductor, it is a hollow space, whereas here you have other charge carriers which are actually blocking them. So E minus E induced will not be equal to 0. Rather, E minus E induced is going to be equal to E divided by kappa, where this kappa is called as dielectric constant. This kappa is called as dielectric constant value epsilon divided by epsilon naught. It is defined as the ratio. It is defined as the ratio of permittivity of free space to the permittivity of a medium to the permittivity of free space. Am I clear with this?
Yes, sir.
Yes. So this is what happens inside a dielectric, unlike whatever happens within a conductor. Okay. So please make a note of this. Okay. Done with this.
Yes, sir.
Yes, sir. Okay. Now see, the next concept that we are going to discuss is capacitors and a concept called as capacitance. So basically, what are capacitors is? If you take two conductors, right? If you take a system of two conductors separated by a dielectric medium, so the simplest definition is you take two conductors separated by a dielectric medium is what is called as a capacitor. Okay. So what will you have? You will have conductor, dielectric medium, conductor 1, conductor 2. So here you will have positive charge. Here you will have negative charge. Are you able to understand this point? This is how
Yes, sir.
the setup of a capacitor is done. So basically what a capacitor does is, till now we understood how the charges are created and the created charges are going to create the fields and the potential. But the question is, where are you going to store that charge? In a device called as a capacitor. Right. So we are going to store all the charges in a device called as a capacitor. So capacitor is basically a device that is used to store charge. And then the charge is stored in the form of electrostatic field. Okay, that's what the concept is. So having said this, what we'll do is observe. So when you talk about the types of capacitors, right? When you talk about the types of capacitors, there are three types of capacitors. One is going to be a parallel plate, and the second is going to be spherical, and the third is going to be cylindrical. So depending on the shape of the conductor, the capacitors are broken into three types. What are they? Parallel plate, spherical, or cylindrical, right? So in our syllabus, we don't have the spherical or cylindrical, we have only this parallel plate capacitor, meaning if you have one conductor like this and another conductor like this, right, which are separated by a dielectric medium, then this kind of an arrangement is called as a parallel plate capacitor, where let's say you connect this parallel plate capacitor across a battery in such a way, you get the positive charge from the left and the negative charge from the right. Okay. So what will happen is the amount of charge that is stored on the plates of the capacitor is directly proportional to the amount of potential difference that we are applying. So Q is directly proportional to V. So when you remove the proportionality symbol, you get Q is equal to C into V, where the C is what is called as capacitance. Where the C is what is called as capacitance. So charge that is getting stored on the capacitor is observed to be directly proportional to the potential difference that we are applying. Means you connect the battery, right? You keep increasing the value of potential. The amount of charge that can get stored is also going to increase. So that Q will be equal to CV, where C is called as the capacitance. And here an important point to be noted is capacitance is the property of a capacitor and does not depend on charge or potential. So meaning what I'm trying to say is, see here, you look at the mathematical expression, right? Q is equal to CV. Sometimes what people understand is, if I keep increasing the charge, will there be a possibility of me to increase the capacitance also? You cannot. Because suppose you take a 1 liter bottle, you take a 1 liter bottle, inside, if I ask you to fill it with some water, what is the maximum limit of water that you can fill within it? What is the maximum limit of water that can be filled within it? In a 1 liter bottle, how much water can you fill?
1 liter.
Obviously 1 liter only, no? Same logic is applicable. For a capacitor, its capacitance is fixed. So you cannot increase the charge that is, you cannot increase the charge on it beyond a certain limit. But one thing that will happen is you can keep increasing the value of charge by increasing the potential, but that will stop at a particular point till it reaches the maximum capacitance. Beyond that, you cannot give charge. So that is the meaning of this statement. This is the property of a capacitor and does not depend on the charge or potential. Is that point clear? Is everyone clear with this?
Yes, sir.
Very good. Okay. So first write down. I'll go to the next concept. See, is my voice audible now?
Yes, sir.
Is it better or the previous one was better? This one is better or both are same?
Now it is better, sir.
No, it's better, no? Okay. No, see. Now the next question next topic that we are going to discuss is capacitance of wait. Yeah. The next topic that we are going to discuss is capacitance of a parallel plate capacitor. So capacitance of a parallel plate capacitor. See, if I take a conductor like this, and if I take another conductor like this, right, both are parallel plates, right? Let's say the surface charge density here is sigma, here it is minus sigma. Okay. So the electric field due to the positive charge is going to be sigma divided by 2 epsilon naught, and the electric field due to the negative charge is also going to be sigma divided by 2 epsilon naught. So if you observe, the net electric field is going to be equal to sigma divided by epsilon naught. First point to be noted. Okay. If I take the area of cross section of the plate to be A and the distance of separation between the plates to be D. I take the distance of separation between the plates to be D, then sigma is equal to Q divided by A, which implies Q is equal to sigma into A, which is Q is equal to sigma into A. Am I clear with this? Or I'll leave it like this. It's a sigma is equal to Q by A itself. I'll leave. Okay. Now listen to this carefully. We know that Q is equal to CV, which implies C is equal to Q divided by V. Right? Which implies Q is equal to sigma into A. Let me call this as 2. So C is equal to, in the place of Q, can I write it as sigma into A divided by, in the place of V, right? In the place of V, can I write it as E into D, because we know that electric field is equal to minus dV by dr. Here I'm ignoring the value of D because in a capacitor, the plates are very, very, very close to each other and the field is uniform. So E, I can take it as V divided by the distance of separation between them, and I'm ignoring the minus sign because I already know the direction in which the field is present. So C is equal to sigma into A divided by what is the value of V? V is equal to E into D. So sigma into A divided by what is the value of E? Sigma by epsilon naught into D. So sigma and sigma will get cancelled. So capacitance will be equal to epsilon naught into A divided by D. Right? It's going to be epsilon naught into A divided by D. Okay. So this is the capacitance of a parallel plate capacitor. So make a note till this point. Are you done writing?
1 minute, sir.
Yeah.
Yes, sir. Written.
Great. Okay. So is right. If you look at this mathematical expression where C is equal to epsilon, the following points are to be noted. The first one is capacitance depends on the medium between the plates. Second, it depends on the area of cross section of the plates. And lastly, it depends on the distance of separation between the plates. So these are all the points that are worth noting. So C depends on the medium between the plates. It depends on the area of cross section of the plates and the distance of separation between the plates. The point clear, guys?
Yes, sir.
So it depends only on the geometry or potential of the conductors. Okay. So the next few concepts: capacitors in series, capacitors in parallel, and then we need to understand what happens when a capacitor is filled with dielectric and is not filled with dielectric. So these are the two major concepts that are left out in this chapter, right? Which I'll cover in the next class, right? Is the point clear? So the remaining concepts I'll explain it in the next class, and then we will solve the problems based on this chapter. Is that
Okay,
all
sir.
clear? Is everyone
Yes,
clear?
sir.
Yeah.
Yes,
So
sir.
now, is there any doubt that you have? Is there any doubt that you guys have?
So actually, when will we get the results for the test? So the results for the test.
Results, sir.
Yes.
We'll get to know by Wednesday or Thursday. We'll get to.
Okay.
Yeah.
Yes.
Okay. Shall we wind up?